Today we're going to talk about discontinuities. There is the removable discontinuity, such as holes. It looks like this. There's jump discontinuity, which is usually from a piecewise function, more than one function put together. And then we have the infinite discontinuity. That is our asymptotes and our limits. So on this page, this first page, we're going to talk about holes, or removable discontinuities. So it says, what are holes and how are they found? It is a break in the function that can be filled in with a point at x equals some number. They are found when factors with variables cancel out in the numerator and denominator. Once they cancel, you set that they canceled equal to 0, and then you solve for x. That's what would go in these blanks. And here's a factoring review. Remember, the TI Inspire, you can press Calculate menu 333, X. Then find the factors given the zeros. So if we have the zeros, negative 2/3, 0, we have x plus 2/3 and x minus 0. So we take the denominator of that 3 and we slide it to the front. So our factored form, given these zeros, would be 3x plus 2 and x. You don't have to write the 0. Okay, if you look at this example, this is the cake method. You use the cake method to factor out the greatest common factor. First, we see if 15 and 40 both have a number that go into them. The greatest common factor in this case looks like it would be 5. Negative 3x to the 4th minus 8x cubed. Now they both have a negative sign, so you can also divide by negative 1, and that changes the signs. They both have an x, so you can divide by x. Now you choose the lower exponent out of 4 and 3. 3 is the smaller exponent, so that's the one you take out. We have 3x to the first plus 8x to the 0th power. So our factored form would be negative 5x cubed parentheses 3x plus 8. The stuff you factored out is your greatest common factor. You multiply them all together. The thing at the very bottom of your boxes, of your cake layers, is what is left over, your remainder. Okay, now let's look at a factoring example. We have 6x squared plus 15x minus 21. First, you want to take out the GCF of these three numbers, which is 3. So if we factor that out, we have 3 times 2x squared plus 5x minus 7. Now we can identify A, B, and C. A is 2, B is 5, and C is negative 7. So from here, we can write A times C up here, which is negative 14, and B, which is 5, down here. We're going to find two numbers that multiply to negative 14 and add to 5. We write negative 14 right here. And we'll write out the factor pairs. We have 14 and negative 1, 7 and negative 2, 3 doesn't work, 4 doesn't work, and 5 doesn't work, and 6 also doesn't work. because those would give you decimals if you divide 14 by each of those numbers. And now we're going to find our differences right here. 14 minus 1 is 13, and 7 minus 2 is 5. We will use the second one because 5 is the b that we're looking for. A is not 1, so we're going to go on to the box. First term, first box, 2x squared. Last term, last box, negative 7. These two middle boxes are your two found numbers. Plus 7 followed by an x, minus 2 followed by an x. Okay, the greatest common factor of 2 and 7 is 1. They both have an x, so you take out the x. They both have a 2, let's take out the 2, and they both have an x as well. If you keep factoring them out, you should get these numbers. So your factored form would be 3 parentheses 2x plus 7, close parentheses, open parentheses, x minus 1. And that's how you would factor. Okay, let's look at these. Name the wholes given the following functions. Factor, cancel, set equal to 0. So we have x minus 1, x plus 3, and x minus 1. These two factors cancel out, so there is a whole there at x equals 1, because if you set x minus 1 equal to 0, x would equal 1 there. Okay, let's look at the next one. If you're to factor this out, you have u plus 2 and u minus 2 at the top in the numerator, and then you have u plus 2 in the denominator. Those two are the same, they cancel, so that means you have a whole at u equals negative 2, because you set this factor equal to 0. Solve for the variable. Let's turn to the next page. So now we're going to talk about asymptotes. That is the dashed line, the imaginary line, the visible line, where the graph never touches. It approaches that number, but never quite gets to it. What are vertical asymptotes, and how are they found? The vertical dashed line on our graph that the function never touches. How to find it? You find after you find the wholes. Set the denominator equal to 0 and solve for the variable. In standard form, it has an h value. So basically, after you cancel out the wholes, which I didn't give you any on this specific page, you will set the denominator equal to 0. You have x minus 5 equals 0. Solve for x, you get 5. So the vertical asymptote would be at y equals 5. Not y equals 5, x equals 5. Let's look at the next one. On this one, these would cancel out, so there's none here. There is a whole at q equals 1, though. Do the rest of these vertical asymptotes. Again, set the denominator equal to 0, and the vertical asymptotes would be at x equals some number. Let's look at the next page. Horizontal asymptotes. What are horizontal asymptotes and how are they found? The horizontal dashed line on a graph that the function never touches. You do this after finding the holes. When the leading term of both numerator and denominator have the same degree, you divide those leading coefficients. When the denominator's degree is higher, the function has a horizontal asymptote at y equals 0. In standard form, it is the k-value. And that should be a y right here. Okay, on number 2, we've already taken out the holes. There's nothing you can factor. The leading coefficient has the same degree as both q to the first power. So then we divide the coefficients. 6 divided by 1 equals 6. So that means we have a horizontal asymptote at y equals 6. And you'll do that for each of these. Since this one doesn't have a w up here, we could think of 0 times w to the second power in the numerator. So that means you would have y equals 0 as a horizontal asymptote. Okay, finish this one. The rest of these ones, your groups are on your own.
1.
What are oblique asymptotes and how are they found? Asymptotes that are neither vertical or horizontal. They could be diagonal or a curve. You find these after finding the holes. When the leading term in the numerator has a greater degree than the leading term in the denominator is when you would have one of these. Use synthetic division or long division to divide the two polynomials. The oblique asymptote is in the y equals found for the quotient. Throw out the remainder. But you do need to have one to have an oblique asymptote. Let's talk about the parts of a division problem. So we have n right here. That's your numerator, also known as your dividend. The number on the outside is your denominator, that's your divisor. The q on top is the quotient. And the r is remainder. Watch the next video to find example 1. When we are not doing decimals, the leftovers are called the remainder. How to divide polynomials with long division. Here's the steps. First, you divide the leading coefficients. Next, you multiply the quotient and the divisor. Third, subtract the product from the dividend. And then bring down the next term and repeat until there's nothing left to bring down. Let's do this example right here. We have x squared plus 7x plus 12 divided by x plus 3. So your dividend, your numerator, goes inside. And your denominator, your divisor, goes on the outside. X plus 3. Okay, the first step, you divide the leading coefficients. So x squared divided by x would be x. We put that on top right here. 1x. Multiply the quotient and the divisor together. So x times x is x squared. X times 3 is 3x. Then we subtract the product from the dividend. So change the sign of each of these. Okay, that's 0x squared. That's 4x. Break down the next term, which is that plus 12. And repeat the process. Divide. 4x divided by x is 4. Multiply. I'll rewrite these up here. Okay, 4 times x is 4x. 4 times 3 is 12. They subtract. Change the signs of each of these. And you have a remainder of 0. So your quotient is x plus 4. There's no oblique asymptote there. Okay, let's look at the next one. We have 15x squared plus 26x plus 8 divided by 5x plus 2. Okay, divide the leading terms. 15x squared divided by 5x is 3x. Multiply 3x times 5x is 15x squared. 3x times 2 is 6x. Change the signs and subtract. We have 20x right here. Break down the 8. So 20x plus 8. Divide 20x divided by 5x is 4. Okay, 4 times 5x is 20x. And 4 times 2 is 8. Subtract. You have no remainder. It's 0. Your quotient is 3x plus 4. So neither of these examples have an oblique asymptote. Let's turn to the next page, synthetic division. So we have special linear factors. Those are factors that have the form a times x to the r minus c, where a equals 1, r equals 1, and c is any constant real number. The remainder will be the numerator over the divisor, the denominator. The quotient will always be 1 degree less than the degree you started with. For example, this first example, we have a degree of 2. After we find the quotient, our degree will only be 1. Our exponent will be 1 in the answer. Watch the next video to see these ones. Okay, let's look at the next page of this packet. Long division with remainder, no decimals. Rewrite as a mixed number. So we have 98 divided by 7. 7 goes into 9 one time. 1 times 7 is 7. Subtract. Get 2. Break down the 8. 7 goes into 28 4 times. 4 times 7 is 28. Subtract them. You have a remainder of 0. Okay, let's look at the next one. 91 divided by 9. 9 goes into 9 one time. 1 times 9 is 9. Subtract. Get 0. Break down the 1. 9 goes into 1 0 times. Subtract 0. You have a remainder of 1. So change that into a mixed number. It would be 1, your remainder, over 9, your divisor. So your answer would be 10 and 1/9. Try the rest of these questions to your packet on your own or in your groups.